So in this review of probability and random variables, we'll be mainly concentrating on random variables and how to use the probability distribution function and the probability density function for some basic calculations. It will be more of a review, as the title aptly suggests. So a random variable, to begin with the understanding of a random variable, a quick recall. A random variable is one whose value is subject to variations, whose value is subject to variations due to chance or randomness, and it is obtained by mapping. It is obtained by mapping every outcome. It is obtained by mapping every outcome on the sample space onto the real axis. So this is what a random variable is. Now, there are, broadly classifying, there are two types of classifications possible. One is a discrete random variable and the other one is continuous. Now, I will give a very simple example of a discrete random variable. This must be sufficient to refresh your ideas of random variables. Let's say that we have a 6-faced fair die. There are 6 faces. We will call, for convenience, we will call these 6 faces. You can sequence them the way you want. There are 6 faces: F1, F2, F3, F4, F5, F6. So you have the 6 faces of this fair die. One way of obtaining a random variable is by directly mapping these 6 faces sequentially onto the first 6 positive numbers on the real number axis. Another way of obtaining, there is no hard and fast rule you should do it this way. The other way of obtaining a random variable in this case is to go for some mapping like this. This is also, you're mapping it onto the real axis. So instead of mapping phase 1 to 1 and phase 2 to 2 and so on, we map phase 1 to -2, phase 2 to -1, phase 3 0 and so on. This is also a possible mapping. So if you see in both of these cases, what we have done is the sample space, each outcome, when you roll the die, you are going to get one of these faces on top. When you are going to get one of these faces facing you when you roll the die. And if you take that as the outcome of the experiment, you are mapping the 6 possibilities, the sample space, each point on the sample space onto a real number. And that is how we get the random variable. This is an example of that. One can think of more complicated examples, which I will not explain here. You can take 2 dice and roll them, and you can map it onto the sample space. Will be having since you're having 2 dice, you will have 36 points possible, and you can map them onto the real number in such a way that you can add them up and map it, or you can subtract the outcomes and map it. Anyhow, that is, I'm not going to do that here. This example should be sufficient to give you an idea what a random variable is, to refresh your idea of random variable. Now x is a random variable X is a random variable now whose value depends on the outcome of the experiment. So if I had mapped the die, the 6 phases, starting from -2 and sequentially going on with -1, 0, 1, 2, 3, if I had mapped it that way, and if I roll the die, I can use X to explain or to express the outcome of the experiment. So if I say X turns out to be 0, that means the outcome is 0. That is, the phase which is mapped to 0 has come out when you roll the die. So this is what the idea is, the idea of a random variable is. Now moving on, a quick recall of cumulative distribution function, or the probability distribution function. So that is, either you can call it as CDF, capital CDF, or capital PDF. It stands for the cumulative distribution function or the probability distribution function. Now, the probability distribution function, of course also called as cumulative distribution function of a random variable X, is given like this: capital P. This is the traditional, this is the notation used, capital P, subscript X, capital X. It is to say that this PDF, capital PDF, the probability distribution function, belongs to random variable X, and the small letter x, the lowercase x, is used to signify a value which the random variable is likely to take. So the probability distribution function is defined as the probability that the random variable x takes on a value less than or equal to x. That means we can also express it as the probability that x takes a value less than or equal to small x. So if this small x happens to be, say, 0.5, the probability distribution function px 0.5 is the probability that the random variable x takes a value less than or equal to 0.5. Now, there is a probability density function, which we usually express in the small letter PDF, lowercase PDF, probability density function, and it is defined as the derivative of the probability distribution function. Now, that being the case, one can show that using simple calculus, it can be shown that the density distribution function, probability distribution function, is related to the density function in this way. So this means that the probability of random variable x taking a value less than or equal to small x can also be evaluated by integrating the probability density function from x, that is from -infinity to x. These are all things which you are supposed to know. This is a review, more of a review. Now, if we take the case of the random variable which we obtained by mapping the 6-phased die, each of the phases onto -2, -1, 0, 1, 2, 3. If we take this example, let's assume the die is fair. Of course, it's a fair die. So the random variable x, if I use now to express the outcome of an experiment of rolling this fair die whose faces have been mapped to -2, -1, 0, 1, 2, and 3, then the probability distribution function of that random variable will be like this. So we'll plot the probability distribution function here. So I have the various possible values which the random variable can take over here, and on the vertical axis I'm going to plot the its capital PDF, that is the probability distribution function. So what is the probability that, so if I try to find out what is the probability distribution function when small x is 5. So basically we are asking the question, what is the probability that this random variable x takes a value less than or equal to 5. So remember the definition. This is the probability that the random variable x takes a value less than or equal to small x. So when small x is 5, it is like, it's akin to asking the question, what is the probability that the random variable x takes a value less than or equal to 5. And in our case, when we roll the die whose faces have been mapped onto these numbers, when we roll that die, it is definite that you are going to get a value which is less than or equal to 5. It's certain. Whether you get 3 or -2 or any of the other numbers in between, you are going to get a number less than or equal to 5. So Px5 is 1. The probability distribution function with small x as 5 is 1. It's a certain event. So that means I can, if I take this as 1, these scales are not matching, so this scale is slightly expanded. So I take this as 1 and Px5 is 1. In fact, you can show that Px6 is also 1, 7 is also 1. So this will be 1. For all values greater than 5, it will be 1. And by the same argument, up to 3, it will be 1. Because if I ask what is Px of 4, it's 1, because you are going to get a number less than or equal to 4. What is Px of 3? It will be again 1, because you are going to get less than or equal to 3 is a certain event. But the moment you cross over from 3, the moment you come this side, say 2.99999, probability of, when you roll this die, the probability of getting a number which is less than 2.999, less than or equal to 2.999 is no longer 1, because the event that has to happen, if you have to get an outcome which is less than 2.9999, less than or equal to that, is you have to have one of these 5 faces turning up. This face, if this is the face that you turn up, if capital X takes a value 3, then your probability of getting x less than 2.999 is not satisfied. So you have to get either 2, 1, 0, -1 or -2, and the probability of that happening is 5 by 6. One of the, so the moment you cross over here, it drops, it jumps to 5 by 6, and it remains so till you reach 2. It remains so till you reach 2. 2 or less than 2. Again, the only possibility is getting these 5 faces. And the moment you cross to the left of 2, by the same argument, you will drop by another 1 by 6, and you will end up getting 4 by 6. And it remains so till 1. You can see 1 or less than 1. Only these 4 faces, only when these 4 faces, one of these 4 faces show up, you satisfy that criteria. So up to 1, from just on this side of 2 up to 1, it is 4 by 6. And once you cross 1, you again drop 1 by 6. You get 3 by 6. and it remains so till 0. And then you cross 0, same argument, you drop by another 1 by 6, you go to 2 by 6, and then the moment you cross over to minus 1, you drop by another 1 by 6, and you reach 1 by 6, and then minus 2, up to minus 2 you remain 1 by 6, because minus 2 or less than minus 2 probability is 1 by 6, because this phase has to show up. And the moment you cross minus 2, it drops to 0. Because if you ask yourself what is the probability that I roll this die and end up getting an outcome which is less than minus 2, the answer is 0, because you will never get less than minus 2. So this is how the probability distribution function of this random variable is going to look like. Now the probability density function, if we plot, of the same random variable, and we know what is the probability, what is the relation between the two. It is the derivative of this that we have to plot here, and the derivative of this from elementary signals and systems course, you know that this is nothing but a series of step functions, and if you differentiate a step, you are going to get impulses. So you are going to get the probability density function of this random variable, which we have obtained by mapping the 6 faces of a Faraday onto the numbers minus 2 to 3. You differentiate at minus 2, you will have an impulse of strength 1 by 6. At minus 1, you have an impulse of strength 1 by 6. At 0, you will get an impulse of strength 1 by 6. And you keep on getting them till 3. Once you cross 3, it's flat. So if you differentiate, you get a 0. And on this side also it's flat. You differentiate, you get a 0. So you get impulses of strength 1 by 6. This is how the probability density function of this random variable is going to look like. Now, having understood this example, having understood what the probability distribution function and density function is through a simple example, having recollected what these two functions are, we will just see how these functions are used further. Suppose we want to find out the probability of our random variable lying between a range of values. Of course, minus infinity to x is also a range, but to be more specific, a finite range of values. We know that this is expressed as probability of the random variable lying below x2 minus probability of the random variable lying below x1. From elementary probability theory, you know this. And this is computed like this. You know the relation between distribution function and density function. So using that, we can write this in this way. And this in turn can be expressed as, which is what we are seeking, probability of x lying between x2 and x1. And this says that this will be 1, because it is a definite event. What is the probability of the random variable taking a value between minus infinity to infinity? It is a definite outcome. So the probability is 1. So any density function, if it is a probability density function, if it is integrated from minus to plus infinity, the result has to be 1. Now there are some important moments. And of course, this is expected value of a random variable, which is the first moment, computed like this. And it is called as the mean of the random variable x. The first moment is called as the mean. It is computed like this. And then we have the nth central moment, which is computed like this, which is the expected value of the random variable minus its mean to the power n, raised to the power n. It is called as the nth central moment. It is computed as x minus mu x to the power n multiplied by the density function and integrated from minus to plus infinity. And the second central moment is an important one. The second central moment, which is computed like this, and it is called as the variance of the random variable, expressed generally as sigma square with a subscript if necessary to specify that the variance belongs to the random variable x. Similarly, the mean is generally expressed as mu with the subscript again to emphasize if necessary that it is belonging to the random variable x. Now the idea of the probability distribution function and the density function can be extended to higher dimensions, and I just to demonstrate, just list down here the case when we have two random variables, joint random variables, so to say. So probability of x being less than small x, where capital X is a random variable, and y being less than or equal to small y, where capital Y is another random variable. This is the joint distribution function of the random variables x and y, which is expressed like this and can be connected with the joint density function like this. These are dummy variables. So the joint density function is small letter p subscript xy, and this is the joint density function, and you can connect the joint distribution function with the joint density function like this. And of course the joint PDF can be computed through a second derivative of the probability distribution function, and of course you can get the distribution function of one of the random variables from the joint distribution function through this operation. And from the joint density function, of course, and of course you can, by the same principle, so these are some, this is an extension of the previously discussed introduced ideas to 2 dimensions. You can extend it to higher, more than 2 dimensions. Now, 2 very handy techniques which we will require, I will just mention them here. I will not derive the details or discuss them in great detail. When the application comes, we will dwell deeper into these methods. First one is the transformation of random variables. I will explain with an example. Suppose we have a random variable x which has a probability density function like this, and we have a second random variable which is a function of this random variable, the first random variable, say x square. Let's say y is equal to x square. y is a new random variable now, which we have obtained by squaring the random variable x, which has a PDF as given here, which is known to us. We square it and we get a second random variable. So we would like to know what is the what is the probability density function of y. So what we do is, in this case, since we know there is a general method also, which I will not discuss now because we will be digressing. This is y equal to x square, and you know how this variation looks like. Now we want to know the probability density function of y. So what we do is we start with the CDF, the cumulative distribution function or the probability distribution function, and this is by definition the probability that y is less than or equal to small y, some value small y. So let's say that small y is here, and we know that this will be root y, this will be minus root y. So now probability of y being less than or equal to, that is the probability of random variable y being less than or equal to small y, is the same as the probability of the random variable x. Probability that the random variable x is in this interval, because whenever x takes a value which is between root y and minus root y, y is always having a value, the random variable y is always having a value less than this. So the probability of y taking a value less than or equal to some small y is the same as the probability that the random variable x takes a value between root y and minus root y. And since we know the density function of x, we can write this like this. We can write it like this, and now this will turn out to be this is going to turn out to be because when you integrate this with the density function, you will get the distribution function, and when you put the limits, this is what you are going to get. Now if I differentiate this, so I will write this here now. I'll get some space. Now if I differentiate this, I will get the density function of y in terms of the density function of x, and that gives us the solution to the problem that we started with. So if I differentiate this with respect to y, I get the density function of the random variable y. When I differentiate this with respect to y, it is like differentiating this with respect to root y and then multiplying the result with a derivative of root y with respect to y. So that gives, this is the result of differentiating this with respect to root y, and then when I differentiate root y with respect to y, I get 1 by 2 root y. When I come to here, when I differentiate this with respect to minus root y, I get, and then I compensate it by differentiating with respect minus root y with respect to root y, and I end up getting minus 1 by 2 root y. That minus and this minus becomes plus, and this is the result of, this is the density function of y in terms of the density function of x. So if you know the density function of x, you have with you the density function of y. Now as an example, let us say that x had a Gaussian distribution. Let's say x had a Gaussian distribution with mean 0 and variance sigma square. Let's say x had a Gaussian distribution. Now if this is the random variable which we squared and got y, then the density function of that will be equal to, you have to substitute x with root y. When you substitute x with root y and 1 by 2 root y, of course, plus again substitute x with minus root y, you get the same thing, and then 1 by 2 root y. So when you add this, you see that since they are the same, essentially it is 1 by 2 of this, 1 by 2 of this, you will get the result as this. 1 by root of 2 pi sigma root y. This is the density function of the random variable y, which is defined as x square, and when x has a distribution, a density function like this. So when the application arises later, we will use this method. So this is just an introduction to the method. There is a general way in which it can be done, in the sense, in general, if you are given like this, what can be, how it can be done, that is how we can get this, that is left to you. You can find that out for yourself. Now, before we end this video, we have to take a look at one more such useful method, a useful tool, so to say. Let's say we have a random variable z, which we have obtained by adding two independent random variables. We have added two independent random variables and we end up getting a new random variable z, let's say. Now, the probability density function of the new random variable z will be a convolution of the probability density function of these two random variables. So if you know the probability density function of these two, namely, if you know this and if you know this, you can find out what is the density function of z. And that is a convolution of these two. Again, I will not derive this, and remember, they have to be independent if this has to work. So this convolution we can write as you know how to convolve two functions. You get it like this. So otherwise we can simply write it is the convolution. And of course, not necessary at this stage, but still, if you work on the Fourier domain, this convolution becomes a multiplication. And if you take the transform of the density function, you will end up getting things like the characteristic function. And if you take depending on the transform that you have taken, you either end up getting the characteristic function or the moment generating function. Anyhow, that is additional information. So this is the review of probability and random variables, a very quick review. Nothing has been discussed very comprehensively here because it's a review. You have studied these things in your lower semesters, so this is only to refresh. So in the next video, we will start with the classical detection and estimation theory.